Hello and welcome to Chapter 12. Today we're going to look at 12.4, which deals with limits at infinity. At the beginning of Chapter 12, we talked about how limits were a very key piece of calculus, and so is finding areas of particular regions. And because we've already looked at how we can find limits in general, we're going to look at limits at infinity because it's the limits at infinity that help us find the areas of regions in calculus. Now, to see what a limit at infinity looks like, let's look at the example where f of x is equal to the quantity of x plus 1 divided by 2x. Now, with infinity, we're going to look at the limit as x approaches a positive infinity of f of x. And if we look at our graph, we can see that as our x values get larger and larger and larger, it looks like our y values are approaching, and we have our graph here set to increments of 1/2. So it looks like as our graph is approaching infinity in the x direction, it looks like our y values are approaching a positive 1/2. Likewise, if we look at the limit as x approaches a negative infinity of f of x, so as my x values get more and more negative, it looks like our y values are also approaching a positive 1/2. So what we can conclude is as x approaches a positive or negative infinity, x is going to get arbitrarily close to 1/2. Now, your actual book definition says that if f is a function and L sub 1 and L sub 2 are both real numbers, then the statements, the limit as x approaches a negative infinity of f of x equals L1, and the limit as x approaches a negative infinity of f of x equals L2, both show the limits at infinity. And to help us evaluate limits at infinity, we can use the given definition here that says if r is a positive real number, then the limit as x approaches infinity of 1 divided by x to the power of r, this really equals 0. And furthermore, if x to the power of r is defined even when x is less than 0, then the limit as x approaches a negative infinity of 1 divided by x to the r is also equal to 0. So for example 1, we want to find the limit as x approaches infinity of 7 minus 1 divided by x squared. Now we can actually use the properties of limits that we learned back in section 12.1. So with those properties, we can go ahead and separate this limit out. And we can separate it by taking the limit as x approaches infinity of 7 and subtracting the limit as x approaches infinity of 1 divided by x squared. So when we evaluate these, the limit as x approaches infinity of a constant is the constant itself, or 7, and the limit as x approaches infinity of 1 divided by x squared, well, if we do direct substitution and we plug an infinitely large number into x squared, I have 1 divided by an extremely large number that's being squared. So 1 divided by an extremely large number in general is going to eventually approach 0. So this is really going to give me 7 minus 0, which would then in turn give me 7. Now, on a side note, when we are evaluating limits at infinity for more complicated rational functions, in other words, if we have something more complicated than 1 divided by x squared, sometimes it's better if we divide the numerator and the denominator by the highest powered term that's in the denominator. So what this does is it helps us evaluate each limit using the limits at infinity. And we'll go ahead and do one of those in the next example so you can see what we're talking about. So for example 2, part A says to take the limit as x approaches infinity of the quantity negative 2x plus 3 divided by the quantity of 3x squared plus 1. And as I mentioned on the previous example, because this is a more complex rational function, I'm going to go through and identify the highest power term in the denominator. So if we go ahead and do that right now, it looks like we have an x squared term in the denominator. So what I'm going to do is I'm going to go through and divide each individual piece by that x squared term. So what I end up with then is the limit as x approaches infinity of a negative 2x divided by x squared plus 3 divided by x squared divided by 3x squared divided by x squared plus 1 divided by x squared. Now when we simplify this, this gives us the limit as x approaches infinity of a negative 2 divided by x plus 3 divided by x squared divided by 3 plus 1 divided by x squared. With direct substitution, I can now go ahead and evaluate this limit. So I end up with, as I plug in an infinity in for x, a negative number divided by infinity is going to give me 0. So we'll say 0 plus 3 divided by an extremely large number or infinity squared is still going to give me 0 divided by 3 plus 1 divided by infinity squared is going to also give me 0. So essentially what I end up with is 0 divided by 3, which gives me 0. So the limit for part A is actually approaching 0. Now in part B, we're going to go ahead and do the same process where we take the limit as x approaches infinity, and I'm going to divide by the highest degree of my denominator. And looking down here, I still have that x squared term. So let's go ahead and divide each piece by x squared. So I have negative 2x squared divided by x squared plus 3 divided by x squared divided by 3x squared divided by x squared plus 1 divided by x squared. Then this gives us the limit as x approaches infinity of a negative 2x squared divided by x squared is a negative 2 plus 3 divided by x squared divided by 3 plus 1 divided by x squared. And if we simplify all of this, now when we go ahead and simplify and we plug in an infinity for each x, we end up with a negative 2 plus 3 divided by infinity will give us 0 divided by the 3 plus 1 divided by infinity, which will also give us 0, or I say I end up with a negative 2/3. And for our final part of example 2, we're going to use the same process. And here we have the limit as x approaches infinity. My highest degree of the denominator is also x squared again. So I have a negative 2x cubed divided by x squared plus 3 divided by x squared divided by 3x squared divided by x squared plus 1 divided by x squared. So now if I go ahead and simplify that, we get the limit as x approaches infinity of a negative 2x plus 3 divided by x squared divided by 3 plus 1 divided by x squared. And when we go ahead and plug in our infinity, I have negative 2 times infinity is really going to give me infinity, plus 3 divided by infinity squared is going to give me 0, divided by 3 plus 0. Now I have infinity divided by 3, and because infinity is not really a case that exists, we're going to say that this limit then does not exist. And this now concludes example 2 and 12.4. Your fun fact, which I'm thinking may be your best fun fact for this year, is the fact that this is your last video, so I'd like to take a few seconds and congratulate you on completing pre-calculus. You guys have all done a great job this year. I've had a good time working with you, and I hope you decide to enroll in AP Calc next year. So this is Mrs. Maurer signing out. Have a good summer, and we'll see you next year.